So Lewis structure for covalent compound. Anytime we have non-metal bonded together, it basically will be forming the covalent bonds, and therefore the molecule form will then be called a covalent compound. So how do we figure out how the atoms are connected together? In order to do that, we need to follow these guidelines right here. So, guideline to draw a Lewis structure for covalent compound. Now remember first that in a Lewis structure, it only shows how the atoms are connected together, but it does not show the 3D shape of the molecule and mainly focus on valence electron because the valence electron are being overlaps to form a molecular compound. Now let's try these steps right here in drawing Lewis structure. And in fact, the best way to draw the Lewis structure of any covalent compound would be to follow this step right here. And don't skip a step. So we're going to use an example of NO3, which is basically nitrate. Now, so the first step is to calculate the total number of valence electrons in the molecule or an ion. And here in this case right here, we have nitrate, which consists of 1 nitrogen and 3 oxygen atoms. So in this case right here, we have nitrogen plus 3 oxygen. And now nitrogen have 5 valence electrons. So therefore that is 5 plus 3 oxygen, and each oxygen has 6 valence electrons. So multiply by 6 equal to 23 valence electron. But don't forget to plus 1 for this negative charge right here. So overall, this molecule right here is minus 1, meaning somehow it has gained an extra valence electron. So if the charge is negative overall, then we have to plus 1 for that charge. So in this case, equal to 24 valence electron total. So remember, add for negative charge and subtract if we were to have the overall positive charge. So going back to this example, there will be 24 valence electrons altogether. So we have done step 1. Now for step 2, we need to determine what is the central and terminal atom in these molecules or ion. And so here are some of the guidelines right here to help us remember which one is central and terminal atom. First, the atom that can make the most number of bonds are always the central atom. An example of atom that would always be the central atom are elements from the groups that can make a lot of bonds. For example, carbon, silicon, nitrogen, and sometimes oxygen as well. But the more bonds that the atom can make, the more likely it is to be the central atom. Okay. And now, next one. Atoms that can make one bond are always the terminal atoms. An example of element that would make one bond would be first the hydrogen, which always make one bond. Now we also see the group 17 element, the halogens. They tend to make one bond as well, but there's exception to them, which we will go over the exception in a little bit. And the next guideline, the atom that is present in the least amount are most likely the central atom as well. So in our example of NO3, we have 3 oxygen and 1 nitrogen. So the nitrogen is the element that we have the least of, and therefore it is the central atom. So that makes the oxygen our terminal atom. And we have 3 of them. So once we have determined which one are central and which one are terminal atom, we would then join all of them together to connect something that we call the skeletal structure by using single covalent bond. So here in this case right here, we're going to put our central atom first, followed by connecting the 3-terminal atom. If we have more than one of the terminal atom, we need to connect them symmetrically, meaning in this case, the 3 oxygens need to be connected to the nitrogen, not as follow. So we're going to put 2 oxygen here and then oxygen somewhere else. So do not do this. Connect them symmetrically to the central atom. So step 4. For each of the bond in the skeletal structure, subtract 2 from the total number of valence electrons that we started out with. So basically, we are using electron to form these covalent bonds. And so we have 24 valence electrons all in this molecule to overlap together to form bonds. And when we draw this skeletal structure above, what we have done is that we have drew 3 single bonds. And this 3 single bond right here consists of 6 valence electrons altogether. So in this case, 24 total starting out minus 6 valence electrons due to the 3 bonds that we drew above, which give us 18 valence electrons remaining. So the step 5, with the total number of valence electrons that are remaining, this 18 right here, then first we use this electron right here to complete the octet for the terminal atom first. And if there's any remaining electron after the terminal atom octet, we will then give them to the central atom. So in this case, let's draw our example again. So this is our skeletal structure. And right now we have 18 valence electrons remaining. And we can see that each of the oxygen terminal will need 6 more electrons to complete the octet. So in this case, we'll be given 6 more electrons. So basically, 3 lone pair to each of this oxygen. So we do the same thing on the oxygen on the left and the oxygen on the bottom. So when we complete the octet for all of these terminal atoms right here, we are using 18 valence electrons. Now, moving on to the step 6. If the central atom are then left with the incomplete octet, we will then use the lone pair of electrons from the terminal atom and move them toward the central atom to form multiple covalent bonds. So in this case, let's draw the structure that we obtained from the step 5 again. So that's what we had from the step 5. And here in this case right here, we see that our central nitrogen do not have an octet of electron. So therefore, to complete the octet for the central nitrogen, we will be moving a lone pair of electron from one of the terminal oxygen to form the double bond to the nitrogen. And here in this case right here, it does not matter which lone pair of electron from which oxygen that we use. We would take one of it and move that in to form the double bond to the central nitrogen. And following this arrow, we will be having this resultant structure. Now, remember, all of the lone pairs, all of the dots are very, very logical, and they're not random at all. And make sure we follow our dots of electron. So that's what we have so far. And that step 7 is to calculate the formal charge. What is the formal charge? The formal charge is basically the charge that arises from certain atoms in the loose structure, because they have more or less electron than the total number of valence electrons that they're supposed to have, and therefore they become charged. So the formal charges of all of the atoms add together equal to the overall charge. So here in this case right here, some of this atom right here may be carrying a charge to them that overall add together to the overall charge of -1. So the charge on some of this atom right here, we then call them that formal charge. So we know that right now the overall charge is -1. So we need to figure out if there's any atom in this molecule right here that could be containing charge in them that add together to this overall charge. And to figure out what the formal charge would be, there is an equation that we can follow. In this case, the formal charge, which we abbreviate with Fc, equal to the number of valence electrons in the free atom minus the number of lone pair electrons that the atom have in the Lewis structure, and minus the number of bonds that the atom have in the Lewis structure. So let's try applying this equation right here to calculate the formal charge of all of the atoms in our nitrate. So let me draw the structure of nitrate that we came up before. So there it is. Now let's figure out the formal charge of some of this atom. So first one, let's say we're going to do the formal charge of this oxygen A. So the formal charge of this oxygen A will then equal to first number of valence electrons in the free atom. So we know oxygen has 6 valence electrons in the free atom, minus the number of lone pair electrons. In this case, this oxygen have 1, 2, 3, 4 lone pair electrons. Now please remember that it's the number of lone pair electrons, not the number of lone pair. So 2 lone pairs equal to 4 lone pair electrons altogether, minus the number of bonds that this atom have in the Lewis structure. And here in this case, this oxygen has 2 bonds. A double bond is considered to be 2 bonds. So minus 2, therefore equal to 0. So now we know the formal charge of this oxygen is 0. So for the same step, let's now determine the formal charge of the oxygen below. In this case, the Fc of this oxygen is again equal to first number of valence electrons in the free atom. For oxygen, that is always equal to 6. Minus the number of lone pair electrons. This oxygen have 3 lone pair electrons, which basically add together to 6 lone pair electrons. So minus 6, and now in this structure, this nitrogen have 1 bonds. So therefore will be minus 1, and thus this equal to negative 1. So the formal charge of this oxygen is negative 1. Once we know that the oxygen on the bottom is negative 1, because the oxygen on the bottom is very much similar to the oxygen on the left side. So that basically means this oxygen is negative 1 as well. And lastly, now let's move on to the formal charge of the nitrogen. So for the nitrogen, here this nitrogen right here, at Fc equal to first number of valence electrons in the free nitrogen atom, which is basically 5, minus number of lone pair electrons. On this Lewis structure, the nitrogen does not have any lone pair electrons, so that is 0, minus the number of bonds. In this case, the nitrogen has 1, 2, 3, 4. It has 4 bonds. So therefore, minus 4 equal to 1, or basically positive 1. So now we know this is positive 1. Now, we're going to be looking at all of this formal charge right here, and we then see that because this nitrogen is plus 1, and this oxygen is negative 1, this oxygen is negative 1, and this oxygen right here is neutral. If we were to add up all of this formal charges, that would then equal to negative 1, which is the overall charge of this molecule. Good. And so down below are 2 of the very important guidelines that will allow us to solve Lewis structure for molecule that can exceed octet. And we will be covering some of these examples as we work through some of the practice problem. So let me for now just restate these 2 very, very important guidelines right here. So guideline number 1, it says that element below the second row can exceed octet. What do exceed octet mean? It basically means having more than 8 valence electrons surrounding it. So if anytime we have a central atom that is an atom that can exceed octet, and we see it has a positive formal charge on it, it will then attract the additional lone pair of electron from the terminal atom to form double bonds until the central atom is no longer positive. And therefore, as a consequence, it can form more than the number of bonds that we would expect, and thus exceeding octet. And guideline number 2 to also remember, if there are more than one types of terminal atom, do not immediately connect both of them to the same central atom. Remember, we need to give electrons and complete octet for the terminal atom first. So forming a bond to a terminal atom is essentially giving an electron to the terminal atom. Let's now try some of the practice problem, and that will give us a chance to go back and see guideline number 1 and guideline number 2 and how that been applied in Lewis structure. So now let's take some time and work on some of this practice problem right here. Let's now try number 1 first. Draw the Lewis structure of NH3. Again, here in this case right here, NH3 consists of all non-metal because both hydrogen and nitrogen are non-metal. So therefore, we know that they be forming a molecular compound. So thus, we need to follow the guideline, the steps, the 7 steps that we have covered in the previous page to draw its Lewis structure. So here in this case, guideline number 1 states calculate the total number of valence electrons. So let's do that first. Step 1. In this case, we have 1 nitrogen and 3 hydrogen. And we know that nitrogen have 5 valence electrons and we have 3 hydrogen, each having 1 valence electron, which then equal to 8 valence electrons altogether. So we finish with the first step. Now step number 2 is to determine the central and the terminal atom. So here in this case we have hydrogen and nitrogen, and because nitrogen can make more bonds than hydrogen, therefore it's very obvious that nitrogen is our central atom. And now we're going to put the nitrogen down first. And now we have 3 hydrogens as our terminal atoms, and because of the same thing, we will be connecting the hydrogen symmetrically around the nitrogen, and that will then be our skeletal structure. And as we draw this skeletal structure, we are using up 6 of out of our 8 total valence electrons because we drew 3 bonds. So here in this case, we had 8 started out, and now we have to use 6 valence electrons to form the skeletal structure. So therefore, we have 2 remaining. Now, with this 2 remaining valence electrons, we're supposed to give them to terminal atom first, if the terminal atom were to need any in order to complete its octet. And in the case of the hydrogen, the state of octet for the hydrogen is duet, which it basically does 2 electrons. And each of this hydrogen now have 2 electrons surrounding it already, so it's happy. So in this case, we now need to give this 2 electrons right here to our central nitrogen atom. 2 valence electrons equal to 1 lone pair, so therefore we put them as 1 pair on the nitrogen. And in this case, we are going to skip the step 5 and 6 and move right on to the step 8, since the central atom now have an octet of electron already. So if we were to use our formal Char equation, we would then see that this hydrogen right here, it would be neutral. So Fc equal to 1 valence electron minus 0 lone pair electron on this hydrogen minus 1 bond equal to 0. So therefore, each of this hydrogen has a 0 formal charge. As for our nitrogen, the Fc of the nitrogen then equal to 5 for nitrogen minus 2 lone pair electron minus 3 bond, which equal to 0 as well, which makes sense because the overall charge of this molecule is neutral. And now if we were to calculate all of the formal charges, that also adds together to 0 as well. So we're good for this one. Let's now try some other example. So let's try number 2. CO2. What would be the Lewis structure of CO2 following our guidelines? How to draw Lewis structure. So in this case, again, the first step would always to calculate the total number of valent electron first. So here in this case, we have 1 carbon and 2 oxygen. Carbon have 4 valent electron and oxygen have 6 valent electron. So that is 12 plus 4 equal to 16 valent electron total. So second step, determine the central and terminal atom. So in this case right here, the carbon can make 4 bonds and oxygen can make 2 bonds. So therefore, it should be clear that oxygen is our terminal atom and carbon is our central atom. And it also makes sense, in this case right here, we have the least amount of carbon. So carbon is our central atom. So we're gonna draw it first. And now we have 2 terminal oxygen. So again, we need to connect this symmetrically to the central carbon. And that will be our skeletal structure. And as we form this skeletal structure, we are using 4 electrons. So we drew 2 single bonds. And that would then give a 12 remaining electron. With the 12 remaining valent electron, we need to give them again to the terminal atom first to complete the octet for the terminal atom. So here in this case, it will be the oxygen. Each of this oxygen needs 6 more electrons to complete its octet. So we need to give 6 to the oxygen on the left and 6 to the oxygen on the right. And that is the amount of valent electron that we have. So now minus 12 equals to 0. So in this case, we do not have any remaining lone pair electron to give to the carbon. And now moving on to the next step. Anytime we have a central atom that does not have a complete octet, we need to move lone pair of electron from the terminal atom to form multiple bonds to the central atom to give the central atom the octet. So here in this case, our carbon right now has only 4 electrons. It needs 2 more bonds, or basically 4 more electrons in order to have an octet of electron. So thus we're gonna take 1 from this oxygen on the left and another pair from this oxygen on the right or left to complete its octet. So in this case, following this arrow, we would be having the following. And now all of the atoms have an octet of electrons. So again, remember that a double bond is considered to be 4 electrons in it. So the next step is to determine the formal charge. And if we were to apply the formal charge equation to each of this atom, we would then find that this oxygen has a formal charge equal to 0, this carbon is 0, and this oxygen is 0 as well, which basically add together to the overall charge of 0. So good with this one. Let's now try some other example. In this case, let's now try number 4. Nitric acid. What is the Lewis structure of nitric acid? So why don't you all take a minute to work on this first, and then we'll go over the answer together. Assume you have a minute to go over this now. Let's now try this problem right here. So again, the first step is to calculate the total number of valent electrons. So here in this case, we have 1 hydrogen, we have 1 nitrogen, and we have 3 oxygen. Hydrogen have 1 valent electron, nitrogen has 5, and 3 oxygen each having 6 valent electron. So that 18 plus 5 plus 1 equal to 24 valent electron. So that is step 1. Now step 2 is to determine the central and the terminal atom. So here in this case, what would be our central atom? So we see hydrogen make only one bond, so that is always the terminal atom. And now we have nitrogen that make 3 bonds and oxygen that make 2 bonds. So we can see that the nitrogen can make the most number of bonds. So therefore that is our central atom. So first we're going to put this down first. So if we were to follow this order, nitrogen is our ultimate central atom, followed by the 3 oxygen and followed by the hydrogen. So therefore we're going to draw the nitrogen first. And now the next to be the central atom would then be the oxygen. So thus take the next to be the central atom and connect that to our ultimate central atom and connect them symmetrically once again. So here in this case we'll be putting one oxygen right here, another one down here, and another one down here. Now where do we now put our hydrogen? If you attempted to put the hydrogen on the nitrogen, that would be wrong, because if we were to put the hydrogen right here immediately, we will be complete an octet for this nitrogen. Now our guideline is again complete octet for the terminal atom first, and as we connect the hydrogens, we are basically given electron to whichever atom that we connect it to. So here in this case, this would not be wrong. Now this is the answer that I think many of you would have. In this case, again, please understand why this is wrong. So let's erase that. So where do we connect the hydrogen then? The answer, any of this oxygen would be fine. And we have one of it, so thus that's the way it would go. And that is our skeletal structure. So here in this case, we just drew 4 single bonds, which is basically 8 electrons. So thus we have 16 valence electrons remaining. And now, what do we do with this 16 valence electron? Again, we need to give them to the terminal atom first to complete the octet for the terminal atom. In this case right here, once we reach this point, we can see that the nitrogen is the central atom because it has all the atoms connected to it. This oxygen now is no longer a terminal atom anymore with respect to the other oxygen that do not have the hydrogen connect to them. So here in this case, we need to give the electron to this 2 oxygen first. Make it this oxygen really the terminal atom, and that is 12 electrons right there. And we have 4 more remaining. So what do we do with the remaining 4? The remaining 4 need to be given to this oxygen right here. Why this oxygen? Because it does not have an octet of electron yet, and it is still terminal with respect to the nitrogen. So therefore, the 4 remaining electrons need to go to the oxygen. And that will then be our skeletal structure. And now next, if we were to inspect our structure, we would then see that the nitrogen does not have a complete electron, does not have an octet of electron yet. So let me draw the structure that I erase again. And here it is. You can see our nitrogen does not have an octet of electron yet. So in this case, we need to now move 1 lone pair of electron from one of the oxygen to form multiple bond to this nitrogen. And here in this case, which lone pair do we take from? So we can take it from either the oxygen on the left or oxygen on the bottom. Why? Because this oxygen have the most amount of valence of lone pair electron, so therefore it will be happy to give it to the nitrogen. So thus we can take either one from here and move that in, or the one on the bottom. Now later on, when we learn about resonance structure, we will then see that for each possible way of where we can take the lone pair electron from to form the double bond to the central atom, each of that structure that we are producing will be called a resonance structure. So in this case, essentially, there will be up to 3 resonance structures that this molecule can have. One will be, so the one will be from this lone pair from the oxygen on the left. The other one is the oxygen on the bottom, and the other one will then be the oxygen on the right side. But in this case, we'll visit that in a little bit. So following this arrow right here, we will be having this structure. So nothing happened to this oxygen. As for this oxygen, it has 3 lone pair before, but now it donated 1, so therefore there will be 2 lone pair of electron remaining. And for the oxygen on the bottom, it will remain the same as well. The only chain that we see in here will then be the 2 electron in here that now been shared between these 2 atoms to form this bond right here. So in here, that's where that electron is now at. And there you go. Now all of the atoms have an octet of electrons. So the next step now would be for us to calculate the formal charges. So in this case, the formal charge of this oxygen right here equal to 6 minus 4 minus 2 equal to 0. And as for this oxygen right here, it Fc equal to 6 minus 1 equal to negative 1. And this one right here, it Fc equal to 6 minus 4 minus 2 equal to 0. And as for this nitrogen, it Fc equal to 5 minus 0 minus 4 equal to 1, or positive 1. So putting in all of these formal charges, we will then see that the nitrogen is positive 1, this oxygen is neutral, this oxygen is negative 1, this oxygen is neutral, and the hydrogen would always be neutral. So if we were to now add all of this formal charge together, it indeed equal to 0. Now, earlier we see that nitric acid does not have an overall charge, but it turned out that it does have formal charges in it that add together equal to that 0 overall charge. So we try another example. Let's now try number 6. And just to go back a little bit, on number 4, that way we begin to see the guideline, the second statement here from the 2 very important statements that I have mentioned to you before. So let me now repeat this again to make sure you understand these important guidelines right here. So the guideline is, again, if there are more than one type of terminal atom, do not immediately connect both of them to the same central atom. Remember, octet for the terminal atom first. So in our case, we have both oxygen and hydrogen to be the terminal atom. And so basically what this guideline is saying right here is that do not connect the hydrogen to the nitrogen, but we need to connect that to the terminal oxygen. So that way we can complete octet for the terminal oxygen first. So that way, again, we have seen this guideline. So hope that will help you guys understand it. Now let's now try this next example right here. So this molecule right here is called sulfate. What is the Lewis structure of sulfate? Why don't you take a minute and give this a try first before we go over the answer together. Assuming you now have a minute, let's now go over the Lewis structure of sulfate. So again, the first step is to always calculate the total number of valent electrons. In this case, we have 1 sulfur, and we know sulfur has 6 valent electrons. And we have 4 oxygen. Each oxygen has 6 valent electrons. And in this case right here, what are we supposed to do next? I hope you see that the overall charge is -2, and because this is -2, meaning the molecule somehow has 2 extra valence electrons. So thus we have to add 2 for that as well. So in this case right here, we have 6 plus 24, which make 30, plus 2 equal to 32 valence electron. So step 2, central and terminal atom. So what would be the central atom? Here in this case right here, we see that oxygen can make 2 bonds. We know that. And sulfur is also in group 16 as well. And we know group 16 make 2 bonds as well. So both of these elements can make 2 bonds. So how do we know which one is the central atom? If you still remember our guideline, our other guidelines state that the atom that is present in the least amount tend to be the central atom. So here in this case, we have only 1 sulfur and 4 oxygen. So that pretty much make the sulfur our central atom. So now we're going to draw the sulfur first. And now we have 4 oxygen. And again, we have 4 of this, and we need to connect them symmetrically to the central sulfur. So 1, 2, 3, and 4. So that is our skeletal structure. And now we have 32 valence electrons at the beginning. And we are using up to 8 electrons as we drill this skeletal structure. So that then gives us 24 valence electrons remaining. So what are we supposed to do with this 24 remaining valence electron? Then the answer, to complete octet for the terminal atom first. So here in this case, each of the terminal oxygen needs 6 more electrons to have an octet. So therefore, 6 electrons equal to 3 lone pair. So we will be given 3 lone pair to each of this oxygen. There you go. And now if we were to add all of this up, that is now 24 electrons. So we have 0 remaining. And now we also see that the sulfur have an octet of electron as well. So we are good. So the next step is now to move on and determine the formal charges. So when we apply the formal charge for each of this oxygen, we then see 6 minus 1 equal to -1. So each of this oxygen is -1. How about the sulfur? For the sulfur, it Fc equal to 6 minus 0 minus 4 equal to 2. So here in this case, it actually is positive 2. So that would be the formal charges of all of this atom. And in fact, if we were to add all of them together, the molecule indeed would be -2. Now, so are we finished with this? Or is there something else that we need to do? And here in this case right here, the central atom in this case has a positive formal charge. And if we remember our guideline earlier, anytime we have a central atom that can exceed octet, and it has a positive formal charge on it, then we need to form more double bonds to it until it is no longer positive. So here in this case, so let me go back to that guideline right here. It's an element below the second row can exceed octet. Sulfur is on the third row on the periodic table, so therefore it can exceed octet. And thus, because an element can exceed octet, it does not mean that it will until it has a positive formal charge on it. And here in this case, we see our sulfur is positive 2. So that meets the requirement to exceed octet. So what will happen then? We will then see that the central atom will attract additional lone pair from the terminal atom to form double bond to it until it is no longer positively charged. So how did that work out in this example? So here in this case right here, because the sulfur is positive 2, that basically means it needs to have 2 lone pair of electrons move toward to form 2 more double bonds to it. In this case, we're going to take one from this oxygen and the other one from this oxygen, or any of this oxygen right here would still be the same thing, but we need to form two double bonds to this sulfur right here. So this is the reason why it is very important for us to determine the formature of the central atom, because this will help us figure out how to draw Lewis structure for substances that can exceed octet. So here in this case, because we know that the formature of the sulfur is positive 2, it will then form two double bonds. So that tends to be true right there, that the overall the formature of the central atoms equal to the number of double bonds that it would have. Follow the arrow in black and we will be having this structure right here. And so if we were to now calculate the formature again, this oxygen would now equal to 0, and this oxygen, I missed out this double bond, this oxygen would also be 0 as well. And as for the sulfur, it is also 0. Now nothing happened to the oxygen on top and on the bottom, so therefore they remain to be -1. And if we were to now add all of these charges together, it would indeed equal to -2, which is the overall charge of this molecule. And now we have the sulfur atom that is neutral, so therefore it will remain the way it is. It will not form any other double bond. If the sulfur were to be still +1, we will have to form one more double bond to it. So thus, again, this is why it's very important that we determine the formature so we know how many double bonds that we need to draw to the central atom. Good. Let's now try another example. Let's try number 7. So why don't you take a minute to try this first before we go over the answer together. So assume you now have done it already. Let's now go over the answer together. So in this case, what should be the first step? And the answer should be calculate the total number of valence electrons. In this case, we have chlorine, and chlorine has 7 valence electrons. And we have 3 oxygen. Each oxygen has 6 valence electrons. And we also need to add one more because the overcharge is -1. So this is 18 plus 8, that equals to 24 valence electron. Oops, I'm sorry, that would be 26, not 24. Let's make sure you have the correct math right there. And now, central and terminal atom. So what would be the central atom and what would be the terminal atom? So what do you think? Now, some of you will be tempted to make the oxygen the central atom. Why? Because oxygen can make 2 bonds, where the chlorine is group 17, and normally they make only 1 bond. But here in this case right here, and this is something important for you to remember, that elements below the second row, meaning if they are on the third row and below, they can exceed octet. And that basically means they can make more than the number of bonds that we would expect to see from the groups. So here in this case right here, this will be an example of when the central atom will exceed octet. And now it do not form 1 bond anymore, but it can make various number of bonds that we don't know until we draw out a Lewis structure. So if we were to again look at all our other guidelines, in this case the chlorines is the element present in the least amount, so therefore that is our central atom. So thus we're going to put the chlorine down first, and now we have 3 oxygen. So thus again, we need to connect them symmetrically to the chlorine, and that's what we would have. So here in this case, we are using 6 electrons to form this skeletal structure, and we have 20 valence electrons remaining. And with the 20 valence electrons remaining, we need to give them to the terminal oxygen, and each of the terminal oxygen will need 6 electrons to be octet. And now that 18 electrons right there to complete octet for the 3 oxygen, and we now have 2 remaining. So what do we do with the remaining 2 valence electrons? We need to give that to now the central chlorine as a lone pair. And now we see all of the atom will now have an octet of electrons. So but are we done? Now don't forget the step 7 right there, calculating the formal charges, because we need to know whether to form a double bond to the central chlorine. So thus calculating the formal charges of the chlorine is very important. So again, once we apply the formal charge equation, we see that this oxygen here is -1, and this is -1, and this is -1. As for the chlorine, the formal charge of the chlorine equal to 7 minus 2, and now minus 3, and that would then equal to +2. So the formal charge of the chlorine is +2. And that means that we need to form 2 double bonds to the chlorine. And we will be able to do that by taking one of the lone pair from this oxygen and the other one from the other oxygen, or the oxygen on the far right. And that would all be the same thing. And following this, we now would have this structure. Oops. Let's keep everything the same. So that lone pair is now used to form the double bond to the chlorine, and as for the oxygen on the left, it now have a double bond over there, and 2 other lone pair of electrons remaining. And there you go, 2 double bond to the chlorine. And now we can see the formal charge of the oxygen on the right side still have not changed. And now the formal charge of the chlorine is now equal to 0. And this oxygen is 0, and this oxygen is 0 as well. And if we were to now add up all of these charges, it will then equal to -1, which is the overall charge that we have seen from the very beginning. So that is the Lewis structure of this molecule. And this is called chlorate, which you guys will learn how to name later. And please try this other example as well, which I will not have enough time to go over with you. And this concludes our lecture on Lewis structure for covalent compound.